Useful functional groups and the reactions that you need to know. Esters. Esters are compounds made from alcohols and carboxylic acids. You can recognise it from its name, which will have the alcohol first part, ethyl in this case, and an ethanoate, which comes from the acid. These need to be remembered that it's always named the alcohol bit first, the acid bit second. The production of esters is via a condensation reaction, sometimes called esterification reaction. It occurs when the hydrogen from the hydroxyl group on the alcohol reacts with the hydroxyl group that's present on the carboxylic acid to give water, and that comes off. The ester link is the COO that you can see mentioned above. As just stated, you can see from the diagrams, the H from the hydroxyl on the alcohol reacts with the OH from the carboxylic acid to give us water. The alcohol, even though it's drawn second in this case, is always named first. The propan 1-ol will become propanal, and the methanoic acid will become methanoate. And that's the same for any alcohol or carboxylic acid when producing these. One type of ester are fats and oils. These are useful in the diet as they contain twice as much energy as carbohydrates do, but they're also very useful for the transportation of vitamins and minerals that will not dissolve in water. These will dissolve in fat, like A, D, E, and K. The structure of fats and oils are very, very similar. Fats are saturated, oils are not. They are both produced by the reaction of glycerol, which has three hydroxyl groups. The proper name is propan 1,2,3-triol, with three fatty acids. These are carboxylic acids, but with long chains of carbons to make up the length of the fat or oil. The difference between fats and oils being that fats pack tighter together with them being saturated, whereas oils don't. So fats have stronger intermolecular forces than oils due to this packing. Soaps are produced by the alkaline hydrolysis of fats or oils. If you just use normal acid hydrolysis, you'd finish up with the fatty acids and the glycerol. Whereas with the alkaline hydrolysis, you're using concentrated sodium hydroxide or potassium hydroxide, which will give you a hydrophilic head, which is ionic, so will dissolve in water, and a hydrophobic tail, which is covalent, so non-polar will dissolve in the oil rather than the water. This allows the soap to allow the oil to mix together. How soaps work is shown. What happens is the hydrophobic tails burrow into the grease, the oil. The hydrophilic heads react with the water, and because the heads are all the same charge, they try and get away from each other as far as possible, a bit like hair on a Van de Graaff generator. This will cause spherical balls of the grease to form. These are called micelles, which will be evenly dispersed throughout the water. Emulsifiers work in a similar way, but rather than having three legs that are hydrophobic, we finish up with only two and one head that's hydrophilic. There are three basic types of alcohols. Primary, where the OH unit is on the end. Secondary, where the OH unit is attached to a carbon that's fastened to two other carbons. And the tertiary, where the carbon is attached to a carbon that is fastened to three other carbons. Here are diagrams of primary ethanol, propan 1-ol, secondary propan 2-ol, butan 2-ol, and tertiary 2-methyl propan 2-ol alcohols. carboxylic acids. These are always numbered from the end where the carboxylic acid is, as you can see here. They will always finish anoic acid. If there is a double bond in there, then there would be enoic acids. Aldehydes and ketones. These both contain a carbonyl group rather than a carboxyl or a hydroxyl or anything like that. This is a carbon that's fastened to a double bonded oxygen. The aldehydes will always finish with an al, and the double bonded oxygen will always be on the last carbon along with the hydrogen making up the last bond. The ketones, the double bonded oxygen, will be on a carbon that's fastened to two other carbons, and they will always finish with the term -one. Here is a selection of aldehydes: methanal, propanal, 2-methylpropanal. And here is a selection of ketones: propanone, 3-ethylpentan 2-one, Moving on to proteins. Proteins are constructed from amino acids. These are their basic building blocks. Amino acids have two different ends. They have an amine group at one side, the N double and the N with the two H's, and a carboxyl group on the other side. This allows for a condensation reaction where a hydrogen from the amine group joins with the hydroxyl from the carboxyl group to give us a peptide link, amide, peptide. You can use either term. You need to be able to spot where these are broken. As you can see there, it's going to be between where the carbon and the nitrogen join. Quite often you get questions whereby you're asked to split up a 4 or 5 different chain protein into its smaller amino acids. During eating, we take in proteins. These proteins are digested. This is hydrolysis, where water is added across the peptide amide link, like it would be across an ester link. This allows breaking up of the proteins into amino acids, like Lego bricks, so they can be reused to build different proteins that the body requires. There are certain amino acids that the body has to take in, though, because we can't produce them ourselves. These are called essential amino acids. Terpenes are responsible for flavours and aromas, spices, things like that. They are unsaturated compounds that are formed by joining together what's called isoprene units. An isoprene unit has 5 carbons, and terpenes will always have a multiple of 5 carbons. So to find the number of terpene units, divide by 5. The correct name for an isoprene unit is 2-methylbuta-1,3-diene. This informs that there's 2 double bonds present in it and a single methyl branch. Terpenes can be found in all sorts of things. They're often used, like say, in flavourings, in aromas, candles, things like that. You can see here you've got a beta-carotene. That's a linear terpene with 8 isoprene units. We've got a methanol, which is a terpenoid which has been oxidised to give us a mint flavour. It is worth remembering when looking at volatility, how fast these things turn into gases, that if they have a long chain, then they're going to be more LDFs, more intermolecular forces holding the thing together than if it's short. Also look for the number of hydroxyl groups present. Ultraviolet radiation can actually split apart molecules. This will leave you with two what's called free radicals. These are molecules with unpaired electrons. These themselves can instigate other free radicals. We have an initiation whereby the molecule is split by ultraviolet radiation. We have propagation, where one of the free radicals meets another molecule and splits that apart, forming a second free radical while joining itself to that. Then we have termination, where a free radical meets another free radical. This can take thousands and thousands of reactions and can lead to a lot of damage to the environment. Into a lot of material these days are put free radical scavengers, as they are called. These are large molecules that will also contain a single or more unpaired electron. When the free radical hits that, then the job of the free radical is to form a stable molecule, and they're stopping the chain reactions.